So, we're going to talk about interpreting hypothesis tests. So a couple issues that depend on how we think about them and how they get used in practice. It'll kind of review implementing hypothesis tests a little bit. And if there's questions on the thing, we'll talk on those. Right? On Friday, we will have class just before spring break, and homework's due then, and we'll start looking, I believe, at some of the things for hypothesis testing, comparing the confidence intervals hypothesis for two groups, comparing proportions, comparing means, and things like that. But first, a little bit more with comparing them. But any questions? Yeah.
On the homework on number 2, do you want us to answer? You kind of made us answer part A twice. Do you want us to answer B as well?
I don't remember exactly what that says. So I have it here.
On the paper, you just say.
Right. So. A twice is fine, right? So the original problem had a sample size of 52, and then I said you could do it if the sample size is 514. So
Okay.
kind of compare that a couple times.
Okay.
But according to what's written here on that, it doesn't say do
part B, so
twice.
you don't have to.
Yeah. So
Okay.
mostly you want to see how it changes.
Okay.
Right? So the larger sample size, you're more likely to get significant results. You're going to have smaller standard error, and so just to illustrate the impact of that.
And when I was doing it on the T distribution, it's like I ended up using, since the 514 is so big, I just used the infinity for the degrees of freedom.
So if you had, so with T and the degrees of freedom, if the table had, like 30 and 60, say, for degrees of freedom, but your actual sample size, say, is 48, right? And then degrees of freedom for n minus 1 is, between there. Right, so somewhere in the middle. So under the 0.025 column for a 5% test or a 95% confidence interval, right, there's going to be these couple of values here. Right? And so you can kind of interpolate between those, or kind of average, or if it's really close. If you're at 31, 30 would be pretty good. Kind of the conservative thing to do, so you don't pretend it's too narrow, would be to go to the smaller one. Right? So if you're 512 and there's like 120 and then there's infinity, and if it's n was 512 or what was it, 524 or so there, and your degrees of freedom would fall somewhere in the middle. The conservative thing is go back to the smaller one, which forces you to have a little wider interval, just so that your intervals don't get too artificially short. Because remember, a property of these intervals is that 95% of them should cover. Right? Or we shouldn't reject a null hypothesis if it's really true, more than 5% of the time. So making it a little bit harder to reject, making it a little bit bigger t-value kind of preserves that property. Really, in an application, you do it on the computer and get things 6 or 8 decimal places and be exact that way. Using the table, it's kind of approximate. So if you kind of interpolate between those values, or even average the t-values between 120 and infinity. At 120, it might be, at infinity is the normal value, so it's 1.96. Because as the degrees of freedom goes to infinity, the t converges exactly to a normal. Right? It has the same areas. And if this thing was, 1.98, well, then I would either use something like 1.97 or use the 1.98 just to be kind of.
So you can use 1.97?
You can use 1.97. Then that's probably reasonable compromise if you're writing a number in there by hand. Right? If you're actually doing it for a real project, you probably use the computer and get the exact value. But the kind of the point of this in terms of interpreting confidence intervals and these is that you want them to at least cover the 95%, or you don't want to make a type 1 error more than 5%, so using the more conservative, bigger values of t accomplishes that for you.
And it's just like your like mu or like plus or minus that.
The t
that's the
value.
whole thing.
Yep.
The t value.
Yep. Times the standard error, so like s over the square root
Oh,
of
times
n.
ten.
Yep. Yep. So sure. Any other questions about it? Homework? So we've done, both of these inference procedures started out with this population, and say we're interested in a mean. We took our sample, and based on sample size n, and we got x bar, and we wanted to go back up here and say something about the mean. And we've had two principal ways of doing that. We did confidence intervals. For the mean, or maybe we do a hypothesis test about the mean equals the mu sub 0 value versus an alternative. Say that it's not equal to that value. Well, these are both are trying to do inference about the mean, so it would be nice if they agree with each other, or in some sense give us the same conclusions about things. Right? So as it turns out, they actually do. So the things that end up in the confidence interval, if any value that ended up in the confidence interval is placed here as a null hypothesis, we don't reject it. Right? So if it's something that the confidence interval says, these are the likely values of mu at a 95%, 95% confidence interval. If we do our test at a 5% significance level, and anything that is in the confidence interval, if that was our statement about the mu sub 0, we wouldn't reject it. And anything that we do reject, any mu sub 0 we would reject is not going to be in that confidence interval. So there is going to be this symmetry that they're both going to give us consistent reports about a particular thing. Why does this happen? Let's say that we're also getting our sample standard deviation, and so we're going to use a t distribution within -1 degrees of freedom. Let's write down the formula. Well, let's write down the formula for a confidence interval and figure out the rejection region and see how they compare. So in our confidence interval, let's say 95%, we had x bar plus or minus a t value, and if it's 95%, we have a t cutoff value. This is the t distribution within -1 degrees of freedom. We want the central 95%, and this is given as the upper 2.5% tail up here. 2.5% down on this side, 2.5% down on this side. Better. This cutoff point here cuts off 2.5% above, and the negative of that is negative 2 n minus 1.025, cuts off 2.5% below, and that's the critical value that gets put in there, n minus 1.025, and we multiply that by the standard error, s over the square root of n. And so any value of mu inside that confidence interval is considered plausible. Right? If we set up a hypothesis test, mu equals mu sub 0, mu is not equal to 1, we rejected mu sub 0 if x bar is too far away. This one sets up the sampling distribution of x bar centered here at mu sub 0. Sampling distribution x bar. Under the null hypothesis. But it's centered right there. And if x bar is too far away, we reject. How far away is too far away? So somewhere out here, this is the rejection region out here. or we get too far this way because it's two-sided projection region. How far away? Well, the distance that's going to be too far away is going to be exactly this distance and a half width. Right? The t value times how many standard error the standard error is. So we're going to reject null hypothesis if x bar is less than, I can write this kind of succinctly. Right? If the distance between the x bar and the mu sub 0, if that's greater than our t in minus 1, 0.025 tail, critical value for the t distribution times the standard error. So any value of x bar that's further away is going to cause us to reject. And this distance here is exactly the same as our half confidence interval. So if our x bar is out here, our confidence interval won't quite reach to mu sub 0. And mu sub 0 would be outside of what's considered positive. So these two things give exactly the same conclusions. Right? One's focusing on a particular value and trying to judge it, but in the end, it's a sampling distribution that's important, and the width of that sampling distribution is that t times the standard error. So it should give us the same things. But any questions? So the same type of thing also works with one-sided things. We haven't really done one-sided confidence interval in particular. So let's look at one numerical example for this. We'll also kind of review doing a confidence interval. So let's say we have some substance that's going for a landfill. And before we can put it in there, we have to test the chemicals that are involved in all this. Right, check its properties. And so let's say this is some sludge wastewater. And we have to look at the pH. And we could ask the question, is the pH less than 7? Maybe for a pH that's greater than 7, it needs to be treated so that it's not so that the acidic. There. And so we take, we have n equals 6 samples. And in these 6 samples, the average equals 6.68 in terms of that pH scale with a standard deviation of 0.20 across those six measures. And so is the average pH less than 7? Right? So one way to answer this is with a hypothesis test, right? We can directly answer that. If we answered it with a hypothesis test, instead of an alternative, null and alternative hypotheses, and so you can say the average pH, is 7 versus the average, is less than 7. Are we convinced that it's less than 7? And if we do that test, we're going to use a t statistic. This is based on a very small sample size. It's a standard deviation computed from the sample. And so our t statistic, x bar minus mu sub 0, right, s over the square root of n. If you put those numbers in there, 6.68 minus 7, and then 0.20 divided by the square root of 6, ends up being negative 3.92. Pretty extreme value for a t statistic. This distance, right, is just 0.32. 20 divided by the square root of 6, or 0.2 divided by the square root of 6, is also a pretty small value. And the ratio ends up being this almost 4 standard errors below, right? Degrees of freedom, in this case, is only 5. And so it turns out that the probability that a t distribution with 5 degrees of freedom is less than this is about 0.006. So that's unusual. That's pretty unusual, pretty extreme. So we can reject null hypothesis and conclude, right, that the average pH really is less than 7. So if that's what we needed to know, then it is true. But we could also look at the confidence interval. And so this would be really kind of a one-sided confidence interval.
Wait, where did you get that 0.006 from?
Well, this would be from looking at a table, right? The 0.006, I'd have to get it from the computer. Do you have the table there?
Yeah.
And so T of 5, what values do you see there?
At the, where on this?
So do you have like a 0.0, what, 1 column?
1.0, or yeah.
What,
At the degree of freedom of,
is 5?
at the 0.01
Yeah,
is 3.365.
3.365, okay. And at the 0.005?
0.005 is 4.032.
0.032. And so the statistic, well, it's kind of one-sided, one tail or the other. That's 3.92.
Oh, that's between the two.
Between the two. And if you go to the computer,
That's what it is.
right, the computer will say that this is 0.006.
Okay. Thank you.
But yeah, so it gives kind of a bound on those. What's the T5 0.05 column? We're doing a one-sided thing, right? We're just going to look at one tail at 5%. What does that number end up being?
2.015.
2.015, right? At infinity for a normal, it was just 1.645 or something like
Yep.
that. So the T5 is, only 6 observations. There's a lot of uncertainty in that standard deviation, so it's much, much bigger. So once we haven't done really examples with one-sided confidence intervals, but we're not really going to compare about the lower side. And maybe we could say this physical measure is only going to go down to 0, but some upper limit up here. And so we're going to get an upper limit by taking the average plus some t-value. In this case, the 5% one with 5 degrees of freedom times s over the square root of n. It's a little bit different than we've typically done in terms of two-sided. Usually we divide this in half. This is degrees of freedom equals 5. 5 in essence. So we got an average of 6.68. And that p-value, kind of the one-sided thing, was, right, this 2.015. 2.015. And then the 0.20 over the square root of 6. And I have the one-sided thing here. What does that turn out to be in terms of that upper limit? Well, the 6.68 plus the 2.015 times the 0.20 divided by the square root of 6 by 6.84. So this is 6.84. So if our interval is basically one-sided, right, it goes up to 6.84. Our average x bar was 6.68. But based on the sampling distribution. We don't think it's going to, the average is really going to be above 6.84. It's clearly less than 7. Right? So based on this interval, right, 7 is not reasonable. Right, at the average. And whether you did the hypothesis test or the confidence interval, right, we're not going to believe 7. Right, we're going to reject it in the hypothesis testing framework, or if we make an interval, it's not going to include 7. If I gave you either piece of information, either summary, it's the same. 7, that's neutral. pH is not reasonable. So if you do problems, most of your problems will be two-sided things, right? So that'd be fine. Use the 0.025 and do an interval. But if you're only interested in one side, you do confidence intervals, 2 focusing on that upper limit. But they're the same, right? So a few questions, right? And so this percent confidence, like 95% confidence, has the corresponding, alpha 0.05, significance level. And there's that corresponding between 100 times 1 minus 0.05 percent. There's a corresponding 5% differences in there. Right? And so in the confidence intervals, we had this thing that if we had the real mean and we get our random data and put in intervals, some of those will cover, we get different samples, we get different averages, possibly different standard deviations, so they might be a little bit different, maybe this one's a little bit wider and still covers. But every once in a while we would get one that would be, either the X bar would be kind of off, or the standard deviation would be small, or maybe in combination, and it would just miss. Right? So we have about a 5% miss. And so if the sampling distribution, and for confidence intervals, here's our mu, whatever it is, about 2.5% of the time, we're going to get an X bar that's out there in the tails. If it's too far away, we reject. I mean, we don't cover the true value. And so the significance levels, whenever we cover, if we did a hypothesis test about any value that's in there, if this was kind of our mu sub 0 is really there, 95% of the time we're actually going to cover it. In this one, if mu sub 0 is true, right, we're going to reject mu sub 0, about 5% of the time. Kind of in our long run experience. And we reject when X bar is too far away. Right? And the 5% where we don't cover some specific value is going to be the 5% where we would make the wrong choice about a mu sub 0. Right? And so they have, the 5% kind of has the same concept of performance. How does the algorithm, how does the decision thing work over time? And so sometimes people ask these questions. If you reject a null hypothesis, does that mean that the alternative is true?
Depends on the alternative, right? If it's just a not equals versus a greater than.
Well, so let's, we could think about any of these cases, right? So let's say you do have an alternative, this, and you had some alternative, whatever it is. So if you reject the null hypothesis, does that mean that? So we have this statement: if you reject H0, then HA is true.
In that case, yeah.
Well, if you reject it, you're going to conclude that HA is probably the better. You're not going to stick with H0. But is it necessarily the case that it really is true. There's a chance you've made an error, right? There's a chance you've got unusual X bar, you know, just by, even if this is really true, 5% of the time, we're gonna make a mistake. Right? So, not necessarily. It's possible, you know, so say alpha equals 0.05, then 5% of the time, this is a mistake. X bar simply is unusual. Unusual by chance. We have to set up a decision rule somewhere to reject something, right? And if X bar is simply 2.5% of the time is a large value in the tail of its sampling distribution, and 2.5% is, you know, we're going to make some mistakes, right? And there's just no avoiding that. So if we reject it, then HA is true. It's not necessarily true, but the decision framework is you go ahead and think, well, the null hypothesis probably is not true. Right? Our evidence is inconsistent with it, and we should probably behave as if things have changed and that there's a difference. But you know, every once in a while we make an error. Kind of a counterpart to that, if you don't reject H0, right, then H0 is true. If you don't reject the null hypothesis, then the null itself is true. Is that an accuracy? Not necessarily again, right? Even if the null hypothesis is false, we could get data that are still consistent with it, right? So not necessarily. Sometimes our data is too noisy, not necessarily. A small sample size, there's big variability, so even if the alternative is right and our sampling distribution is really different, we can have some variability, right? So there's a picture, right? So, you know, if here's mu sub 0, in the first one, every once in a while we get a value of X bar that's you know, kind of funny and out there. But even if the alternative is true, right, the alternative might generate values of X bar that are close to mu sub 0 and we wouldn't reject it. But that doesn't mean that mu sub 0 is true. Yeah.
Is this also 5% of the time? That not necessarily?
Not necessarily. It's not necessarily. It's kind of, it depends on how extreme that is, and that kind of ties into what is power. And we're going to talk about power. But there's a type 2 error. So type 2 errors, right, do happen. This first one, when you reject the null hypothesis, even if it actually is true, is a type 1 error. Hypothesis testing gives these two things different. First, we consider this set up null hypothesis, don't reject it too much. That becomes our first goal. But a second goal would be, if the alternative is really true, we do want to get rid of the null hypothesis, and so we don't want to make that error. Small sample sizes, it's hard to reject. If the differences between things really are quite small, it's very hard to detect a difference like that. And that gets into the sampling distribution. So I guess we'll just talk about it. So power is the probability you reject the null hypothesis if H0 is false. And generally we want large power. Power is related to something called beta. beta is the probability that you fail to reject H0 if H0 is false. And this is what is this type 2 error. We set up our testing procedure, our decision procedure. We don't want to reject the null hypothesis if it is in fact true, so we make that 5% by choosing the 5% tails. But we also want a pretty good chance of rejecting the null hypothesis if it's true, right? Maybe you have to reject the null hypothesis to publish something, to get people to change behavior, to change government standards or adopt a new technology, right? So you want a small type 2 error, and where these things come from, kind of a picture illustrates this. So if the null hypothesis says it's mu sub 0, we're going to choose a significance number, alpha, to determine our rejection region. So alpha leads to the rejection region. And so let's say, we're going to reject if the null hypothesis, anywhere up here, continuing on, or if x bar is back in here. Right? If you get an x bar over here, or you get an x bar right up here, you're going to reject the null hypothesis. And if alpha equals 0.05, under the sampling distribution, that's about 2.5% there. And going all the way on here for infinity, right, it's about 2.5%. So we choose the alpha to get this rejection region. Now what power is, if H0 is false, right, and let's say we have a mu sub A here, right, the power is if that's where it's supposed to be, if that's the truth, right, then our sampling distribution is going to be different. Right? It's going to be centered over there, it's going to go down something like this, really small on this side. And power is going to be the probability we're in that rejection region, but under the red curve. So under the red curve, right, at this point, it goes up to there. And up here, it goes down to here. So power, in this case, is this little area, which is, on one side, is almost nothing, like usually, right? It's almost all on one side. I'm going to erase this 0.025 so it can get covered up here. Maybe I'll draw it like these type of things, right? So it's this whole area out here. So the red area is equivalent to our power. Right? And so it's the probability we're in the rejection region under the alternative. And we want that to be as big as possible. 80, 90% would be great. But a few things affect that. Right? Certainly this distance does, because if you push this out here, right, you get a bigger distance there. If the curves were well separated, this is mu sub 0, and this is mu sub A, and this is our rejection region, is all that, or under here. This is our rejection region, and our rejection region goes here, right, all the way up. And this is the truth, that we're really going to be out here, right? There's basically 100% if I draw this, right? Basically 100% power here, because all of our x bars under the alternative are going to be way out there, right? So as these things separate, it's easier to get, your data are going to tell you, your data are going to be farther away from the null, and you're going to get a big probability that your actual x bar is going to be way out here in the rejection region. That's almost too extreme to draw it, right?
And you said that's a good thing?
That's a very good thing, yeah. So if you're trying to reject the null hypothesis, right? So here's the HO. The HA says it's different. If specifically it's out here, you're very likely to reject. It's very hard to not reject that. So either that is either achieved with difference here. Another way that curves like this get separated is if there's a real small standard error. So if there's a really big sample size, right, each curve becomes narrow, the kind of standard deviation the standard error difference between these two means, these two values, becomes bigger, right? So like S over the square root of n, small, which happens if n is big. It also happens if the standard deviation is small. So if you can get a better measurement, thing, and there's less noise there, or you restrict your hypothesis to more specific groups, and it's not kind of a mix and a more variable population. Sometimes you can test in subgroups that are more homogeneous, and it's not so mixed. But in any case, you get that. But we can calculate power in these cases. Right? So as an example, let's do something where we're measuring height above the ocean. We're on a boat or on a plane or something flying across the ocean, and this thing has GPS and a measurement of the level that we're at. Say you're a biologist going around on islands and measuring the height of the islands and what's living there, like studying species that might be around Galapagos Islands or something. Some of the islands are just barely above the sea level, and some pretty high hills on them. Right? And you're looking at the flora and fauna and the animals that are around there, and you're interested in at what level they're growing. Right? So let's say that there's 1,225 measurements of this, and then 926 of them are within acceptable tolerance. Levels, that they're plus or minus a certain amount. And the goal for the measurement instrument is 75% accuracy. Does this tool achieve, is it better than 75% accuracy? Is this measurement tool more than 75% accurate? Hypothesis test about a proportion. This one's really kind of phrased as a one-sided thing, right? But so if we wanted to test this, all right, we could look at the null hypothesis that we're 0.75. Our sample proportion he had is 926 over 1225. About 0.754. So it's a little bit, or 756, sorry. So in fact, the rate we achieved in our sample is a little bit above that. But do we reject the null hypothesis? Is it really above 0.75? Are we convinced, based on these 1,225 measurements and actual determinations, that we're really accurate? So, an alternative, the greater than 0.75. Well, with proportions, we use normal. And this one-sided going bigger is we're going to reject the null hypothesis if our p hat is greater than 0 plus a 5% tail, 1.645. P0, 1 minus P0. N is our formula for standard error for proportion. And so this will be our 0.75 plus 1.645, 0.75, 0.25 over our 125 measurements that are in there. And sometimes I do these in my notes one way, and then I start doing them another way over here, so I don't always have the answer. So if we did the 0.75 plus 1.645 times the square root of 0.75 times 1 minus that over 1,225. If it's greater than 0.77, we would reject. So we're going to reject if it's greater than 0.77. Can we reject the null hypothesis? 0.754 is awfully close, right? It's not bigger than this, so we do not reject. H0, it might be 75%. Can't prove that it's better. So if we have, the standard that people can achieve now is 75%, and we have this new technique, we haven't really proven that our new technique is better. What's the chance? Yes?
Where did you get 1.645?
So under a normal, under a standard normal, this normal 0, 1. In this case, doing a hypothesis test one-sided, looking at something that has 5% above. So that's the, up here, the 95th percentile of a standard normal. It's right between 1.64 and 1.65 on the tables. So there was a normal table, and so that was just about the cutoff, just about 95% was at that point. So, and so if we look at we could look at a normal table. What's T normal? There it is. So for the normal, if we want to get a z value that cuts off a certain percentage area, right? And then we go down, it's on the second page of this thing, right? So 1.60, 1.61, 1.62, 63, 1.64. Sometimes you can, it's not going to let me highlight those. Do you see these? Oh, they're good. But those couple numbers there, that's just about 95%. Between those two. Right? So that's in the 1.6 row, and it's between the 0.04, 0.05 columns. So it's about 1.645. And with a one-sided thing, we just look at a 5% side instead of the 2.5% side. We needed a 2.5% side. Our 1.96 number. Right? Here was the 95 plus 2.5. Here's the 0.975. Right? So 1.9 row and then the 0.06 column. That's where we got the 1.961. And then the other one was between those two probabilities. It's right in here is the 1.645. So power S was a chance that we did reject, that we would have had to reject. So we're going to say, well, so we'll say the null hypothesis is that P equals 0.75. Right? When do we reject? Well, we have to have something at P0 plus, we just work this out. We reject if p hat is greater than p0 plus a a normal value, P0, 1 minus P0 over n. And that ends up being 77. If the alternative actually was where our data said it was, if our alternative really was 9.754, so it is bigger. What's the probability we would be greater than 0.77 if that were the truth? What's the chance we would reject and we would be bigger if that were the truth? We calculate what's the probability that p hat would be greater than that 0.77 under this hypothesis. So if p hats are a statistic and the truth is 0.754, what's the chance that we get a sample proportion greater than our rejection cutoff? So in our the pictures of power, right, this is that one. This is in terms of means, but if this is our 0.75 as our proportion, and here's 0.754, our alternative, this cutoff up here is 0.77. So what's the chance that we're out in that tail essentially, right, under this alternative? So this becomes a second normal calculation, right? P hat's approximately normal, so we take our 77 value minus our 754 average. Now the standard error under this one, right, is 0.754 times 1 minus that over our 1225 sample. And, 756, I'm sorry. I don't know why I have that in my mind. 754. The number 756. The chance that you're bigger than that, this turns into a z value, the chance that you're bigger than 1.17, that's not very likely, right? To be above 1 standard deviation above that, that's only about 12%. That wasn't very good, right? So if the truth is at 0.754, and we've done 1,225 tests, 756, right? The chance that we would reject 0.75 is really quite small. We have to be really lucky to get something up there. But most of the time we're not, even if the truth is really a little bit different. So power is kind of low in that case. Right? What if we had a bigger sample size? Well, let's do that, a bigger sample size first, because that changes two things, actually. So again, the null hypothesis, let's say that's 0.75, and our sample size is 1225. So we reject, we're doing alpha equal 0.05 one-sided. So we reject if p hat is greater than 0.77. Well, what if the truth really was it really was 0.77? Here's what we have. Right. Well, what if the truth? What if HA? What if it really was 78%? What if there really was a bigger difference? And our mechanism, our new measurement was really better. What would be the probability we would reject 0.75 based on a new sample of 1225? if this were true. Then, we reject still at this level, the probability we reject null hypothesis, given that the alternative is true, is the probability that our p hat is greater than 0.77. So that was determined only by the null and our sample size and the fact that we're doing one-sided. Right? If p hat under these scenarios is greater than 0.77, we get a rejection. Yeah.
So that's the new p hat next to HA.
This would be the new p alternative, right? So if that's the alternative truth. Right, so we haven't seen p hat for this. So power calculations sometimes are done without data. You don't necessarily know the data. Right? Kind of the power, if our sample point had been right on and it had really matched the truth, and the truth was a little bit different. Even if it was a little bit different, there's a very small chance of actually getting a p hat that in a sample is bigger than that. Right? So in this scenario, the null hypothesis is 0.75. So we're going to reject if it's greater than 0.77. Now we're asking the question, well, if in reality our new device for measuring these heights is more accurate and the rate of success is 0.78, will we be likely to reject the null hypothesis? Do we have high power? So it's a now we do convert this to a standard normal. 77 minus 0.78. We use our new alternative out here. So 0.78, 0.22 over 1225. And I have some numbers here, but I'm not completely sure. There's a couple of things that change. So let's just double check. So what is that z value going to be? 0.77 minus 0.78 divided by the square root of the variance times 0.22 divided by 1225. Negative 0.84. The chance that a normal is bigger than 0.84, p norm gives us below negative 0.845, is about 80%. So let's put these numbers in there. So the z value, we're standardizing, turns out for power is probability that z is greater than negative 0.84. And that probability is about 80%. So 80%. The old device is at 0.75. We would reject that and say we're better if our sample is actually above 0.77. If in reality our new device is better and it has a 0.78% response, right? And we do this test, we would think that 80% of the time in testing in this type of situation, we would reject. That's a pretty good chance of rejection. Probably justify doing the study. The power is a little bit of a tricky thing, right? To look at. The way if we write things out, so the picture, right? Again, is we have two things here. If the null hypothesis is 0.75, we're asking what's the chance to reject the 0.75 if that particular alternative is true. Right? If it's really 0.75, we're going to get proportions in here. Once in a while, we're going to get ones that are out in the rejection region. So if 0.78 is the true, we're going to get big values a lot of the time. More than 80% of the time, it's going to be big enough to reject. So if you put these things into formulas, let's do it into kind of one particular formula. Let's imagine a two-sided hypothesis. So we would reject the H0 if our sample proportion is greater than P0 plus 1.96. Now I'm using 1.96 because of the two-sided. then the standard error P0, 1 minus P0, yeah. For root 4, p hat is less than 0 minus 1.96. So the null hypothesis and the type of test we're doing sets up these rejection regions. Now we can assume, what if this is false and there is a true value under the alternative? What if it's true? Well, then we should reject the null hypothesis. What's the chance that we reject the null hypothesis? What's the probability we reject? Power is the probability that we reject. So it's probability, and we're in these rejection regions. So we have greater than P0 plus 1.96, P0, 1 minus P0 over n, plus the probability that P hat is less than P0 minus the lower value. Assuming it's PA though, we're going to convert these two things to z-scores. But where the mean or the rate is really PA. We're going to P0 plus 1.96, P0, 1 minus P0 over n. So do all that. We're going to subtract the true value, capitals, and divide by the standard error under the alternative. PA, 1 minus PA over n squared. That's going to give us one probability. And if we standardize this one, standardize z-score, the value we're standardizing is this. We're going to standardize that one under the alternative. Right. So subtract A divided by PA, 1 minus PA over n square root. And that's going to be our power. So yeah, kind of a little bit complicated, right? 'Cause, you know, it's embodied in, right, the picture, right? We initially choose the rejection regions. That's the first step, and then calculating the areas under, below this or above this, but under that other curve. So that's why there's this second standardization. There's this. Did it add a page for me? Is that my last?
Can you just
Oh,
scroll
there
down?
it is. Yeah, right. I just scrolled. Right. So it's a little bit more involved because there's more things going on. But at this, you can look at the chance, that you would reject, and figure out, should you do this. This can also be turned into, sample size planning. If you have a null hypothesis like P equals something, and you have an alternative that says P equals P sub A, right? And you want to do an alpha, say 0.05 level test, you can ask the question, what sample size do you need? To have, say, 80% power reject H0. And so there's some formulas in there, but just as kind of a couple of examples that comes out of this. So if you had a null hypothesis at a proportion of 0.5, and an alternative says that it's 0.6, and you want, and you're going to do an alpha 0.05 level test, and you want 80% power, the formula works out that you need to get a sample size of about 152. On the other hand, if the alternative is smaller, my handwriting's worse if I don't stand this way. If you try and detect a difference that's narrower, right, then the sampling distributions under those two things overlap a lot more. And you're unlikely to be really high. Your statistic isn't going to be nearly as high typically under this one as it is under this one. It's that alternative from this one. So you need to compensate by shrinking the sampling distribution, by making it narrower. So you need bigger N. And so if you do the same thing, N under these scenarios goes up quite a bit. It goes up to 615. It's about 4 times as big. You're trying to detect half the difference, right? 0.1 versus 0.05 difference in there. So the standard error has to kind of cut in half, and so the sample that you require to have a pretty good chance of success gets multiplied by 4. Right? So we'll do a little bit of that with, I think for us the idea of power and required sample size mostly will be qualitative questions about how things affect the sampling distribution, right? Rather than implementing so many of the formulas. But the book does give them there, and then it would be good to use those if you're doing a real study. But anyway, it becomes one further interpretation or thing to think about with the hypothesis testing. Mostly we're going to stick to the basic questions. You have some data, do you reject this hypothesis or not? If you don't, why didn't you? Maybe it's an error. Maybe you started out with very small sample sizes and didn't have a good chance, and things like that. So. All right, we'll stop there and then come back. What? That was the one you sent to David later. No, you got most of it.
It took a long time on it.
Yeah, me too.
Yeah, it took a long time.
I wasn't even sure I was gonna make it to class today. Yeah, she doesn't notice.
I think it's
The last 3 questions. Yeah, I know. How did she in class take it? There's no way they could finish. Except for Luke. There was, what you get for the last one? For the E1 and E3 or E? Yes, E1 and
Doing
E3.
it, and I wasn't sure whether it can achieve AR sample or something.
So it was like E2 is 20 volts. I don't remember
N times
exactly what it was.
P0,
I know that
they were
E-
high, like
yeah,
10
they're
and
big.
90.
84 volts.
That's probably good enough.
Large, but then like
40
if you
or
multiply
something.
it
Yeah.
It was
by
like spaced out. Okay.
like
It was weird today.
0.1,
Yeah.
it's like
I didn't know
turns
how, I
to
knew the
9.
answer was.
Yeah, and
for the
so,
other one that was like
you know, some people would,
and R.
Yeah.
it's all
I
kind
knew
of
it was
qualitative.
9 and 1.01.
The bigger that
I
gets,
just did the math. I used
the more accurate
Start
it will
plugging
be
into
from probability.
Oh
That's
yeah, you went
probably-
backwards, right?
It was just like
That's
the
what I
same
did too,
with
because
like this.
I knew,
And then I double checked on the two.
Yeah.
Right, but that means
Yeah.
it depends
I didn't know how to get the